So, hello everyone and welcome back. Let's just get back right in where we left off last time. Share my screen. Work? Nope. All right. Good. Now, let's get started here. So last time we have finished off with the what is now called textbook RSA scheme, where the public key consists of this modulus n and this exponent e. Modulus n here and this exponent e, and this n is just the product of two large primes. And e and d are inverses modulo phi of n. So to encrypt, we just compute m to the e mod n, and to decrypt, we compute c to the d mod n. And correctness follows from the fact that second, let me silence this. 2 hours, good. All right. Correctness follows from the fact that E is an inverse, or D is the inverse of E modulo phi of n, and that in the exponent, we essentially compute modulo phi of n. Okay, there's a question. The trapdooriness of RSA arises because of the Totian function, right? That's correct. So the essentially, let's put it another way. If I were to give you phi of n, somehow in the public key, for instance, then RSA would be easy to invert. Right, so given phi of n, there's no hardness left in RSA. But we're going to get into the RSA into the RSA scheme or RSA assumption a little bit later. So there's another question on the chat. Why do we compute in z phi of n instead of z n star? Can someone from the audience answer this question? So we actually compute in z n star, right? Let's say our m is in z n star, but why can I reduce modulo phi of n in the exponent? Can someone answer this question? So phi of n is n star is the order of z n star. That's correct. So this is essentially because of the theorem of Lagrange, which says that in a group of order whatever, in this case phi of n, right? Phi of n is the size of this group or the order of this group z n star. Or when we do exponentiations, we can reduce modulo phi of n in the exponent. Good. That's why we're computing in z phi of n, because this e times d happens in the exponent, and there we are allowed to reduce modulo phi of n. All right. Let's go further and quickly reflect about the security of the basic textbook RSA scheme. So there are really many problems with the scheme as presented here. Now, the main problem, which shouldn't come as a surprise to you, is that encryption is deterministic. To encrypt, I just compute m to the e. M is my message, e is let's write mod n, right? E is in the public key, so there's no randomization whatsoever in encryption, which means that such a scheme cannot be in CPA secure. Right? For now, in CPA security was kind of the gold standard for us, or one of the gold standards for us to evaluate security of a scheme. If we have deterministic encryption, then different messages encrypt to different ciphertexts, guaranteed. And I can just test this message ciphertext relation by given a message, just encrypt it and see if I get a certain ciphertext. So I can really be certain if a ciphertext encrypts a certain message, which is bad, which immediately contradicts in CPA security. Good, yeah. This just says we can test whether a ciphertext encrypts a message M by re-encrypting this ciphertext. But there's also other problems. Maybe these problems are features in disguise, actually, with textbook RSA. So one famous example is, let's say in textbook RSA, I'm getting an encryption Z of a message M. Then one thing I can do publicly is, given the public key, I can compute 2 to the E and multiply this with C, reduce it modulo N, and by correctness of RSA, this is just a routine calculation, this will be an encryption of 2M. So textbook RSA allows me to convert encryptions of actually any message M into encryptions of any multiple, any known multiple of this message M, right? Not just 2. I could have used any, let's say T. I could have multiplied C with T to the E and gotten an encryption of T times M. So security-wise, of course, this is a problem. This is highly malleable, but in other settings, this is actually it can be used as a feature. So certain aspects of encryption schemes, which first, or of cryptographic primitives, which first come in the form of a problem, actually later can be used to get some security properties which are otherwise hard to achieve. And this is, for instance, here because of this group homomorphic property of RSA. So RSA encryption, or textbook RSA encryption, is in fact a group homomorphism. In fact, a group automorphism, or yeah, it's a group automorphism. Good, and maybe, let's see if we have time, we will return to this later. But now, since as we've seen this first example of the, let's say, first ever published public key encryption scheme, let's look into defining security for public key encryption. And of course, we will draw inspiration from our security definitions that we had in the world of private key encryption, and just do the necessary modifications, but always keeping in mind what resources do we give to the adversary, or what resources should we give to the adversary, and what should be the goal of the adversary's attack. All right. So what we will do is we will define in CPA security for public key encryption, and not analogously to the definition of in CPA security in the private key world. So really the main difference here, or the main difference which actually simplifies things for us, is that the adversary A additionally gets the public key PK, right? As the name suggests, the public key PK is public. I'm putting it on my homepage, so I couldn't possibly assume that this public key is hidden from the adversary. So we have to definitely give the public key PK to the adversary. This actually simplifies things a bit. Now that the adversary has the public key, we don't need to give an encryption oracle to the adversary because he can just produce ciphertexts all by himself using this public key, right? So even if we gave him an encryption oracle, he could just simulate it himself. So in other words, let's say I had an adversary who wants a decryption or encryption oracle, sorry. To this adversary, I can simulate this encryption oracle by an adversary who doesn't have one, who just gets the public key and uses this public key to simulate the encryption oracle. So that's actually a nice thing. And in fact, as it turns out, this notion of INCPA security was first defined for public key encryption. It wasn't called INCPA security at first, but rather semantic security, and defined in a slightly different but equivalent way. But this whole idea of defining security of encryption schemes via these games that capture resources and attack goal actually comes from the world of public key encryption. So you're seeing somehow in a way the entire lecture here proceeds in a historically inaccurate way, because private key encryption has been around for long, but the proper security definitions, well, we first had to wait for the arrival of public key encryption before people really started putting deep thought into how should security be defined. Because here in public key encryption, even small modeling problems can lead to really severe security problems in the in schemes that are later deployed in the real world. And this has happened. This has happened quite a few times. Okay, so let's look at the INCPA experiment for public key encryption. As usual, we have an adversary and a challenger. The challenger creates a pair of public and secret keys. The public key is given to the adversary. Now, think of instead of an encryption oracle. In the private key setting, the adversary gets access to an encryption oracle. Here, it's sufficient if we just give him the public key. With the public key, he can, if he wants to, simulate an encryption oracle to himself. Now, at some point, the adversary announces two messages, as always, M0 and M1. Challenger flips a bit, encrypts one of them, MB, gives the ciphertext to the adversary, and as usual, the adversary has to guess the bit B. If he guesses correctly, he wins, otherwise he loses, and we call the output of this experiment INCPA of A. So really, INCPA security is slightly simpler in the case of public key encryption than for secret key encryption, because we can just do away with this encryption oracle, not needed here. Of course, the formal definition says an encryption scheme, keygen encdec, is INCPA secure if it holds for every PPT adversary A that there is a negligible function nu, such as for all security parameter in N, probability that A wins this experiment is 1/2 plus nu of security parameter. Really the analogous definition to the private key setting. Oh, okay, here, that went too fast. So here the build sort of came automatically without building this up, but okay. So as a first encryption scheme, we will look into the so-called El-Gamal encryption scheme. The El-Gamal encryption scheme is essentially, in hindsight, just the Diffie-Hellman key exchange turned into an encryption scheme. There's really not a lot to it. So if you understood or if you got what was happening in the Diffie-Hellman key exchange, sort of the same thing is happening here in the El-Gamal crypto system. So the algorithms are given as follows. Keygen first generates a cryptographic group G of prime order P, roughly 2 to the security parameter, and a generator with a generator G. Okay, next thing. By the way, oftentimes these are so-called public parameters. In that keygen doesn't really generate a new group each and every time we generate a new key pair, but this group is sort of generated once and for all, sometimes by a standardization authority. Does anyone know a certain group which is used particularly often, or which is particularly popular in certain open source implementations and actually widely used? I mean, I know there's a few real cracks here in the audience, so probably you've heard of this group. No one? I'm just trying to get the name right because I wrote it wrong in the past. Let me just check. Ugh. Now my mouse pointer is whoops. It's okay, now Google is failing me to oh, come on. No one in the yes, good. Someone wrote it, curve 25519. This is the Edwards curve at 25519. I got the 255 wrong. Happens to me once in a while. Thank you. So we had someone EG at 25519. Actually, this okay, maybe the person who wrote the correct answer at 25519. Do you know what this 25519 means? What does it stand for? And someone asked, is it based on efficiency or what? Actually, yes. Generating a new cryptographic group, especially if it's an elliptic curve group like this Edwards, this Edwards curve, is really inefficient. So where is someone is asking, where is the difference between ed 25519 and curve 25519? I'm not the utmost expert, but I think it's the same. And ed just stands for Edwards curve. This is a special type of elliptic curve. But here's the thing: what this 25519 is decoded for. The order of this group is 2 to the 255 minus 19. It turns out that's a prime number, and I mean, we want prime order groups. Everything. I mean, for most applications in crypto, but this 25519 just is a shorthand for the order of this group. Someone writing it's 32-bit only? What do you mean with this? I mean, 2 to the 255, I mean, a number of size 2 to the 255 doesn't fit into a 32-bit register. Oh. Good. I think when it says it's 32-bit only, it means that the group operations can be implemented with 32-bit logic. So there's sort of a nice way to map the group operations to instructions that are supported by the processor. But the order of the group is roughly this 2 to the 255. And this is, I mean, too big for a 32-bit register, right? Into a 32-bit register, you get at most 2 to the 32 numbers. What's a very large number? 2 to the 32. I would say 2 to the 32 is a small number. This is, I mean, roughly 4 billion. Yeah, 2 to the 255. Yeah, that's a very large number, but in terms of crypto, it's actually a small number. That just means that you get roughly these 255 bits of security. For private key, in the private key world, that's a lot. 255 bits of security in the private key world is a lot, but compare that to RSA moduli that are typically proposed. There you have moduli that are of size 2 to the 4096, right? That's, I mean, an order of magnitude bigger than what you have for this group. So this is actually, I mean, getting ahead of ourselves here, but this is actually very small for public key crypto standards. So this is I mean, you're typically not getting keys and ciphertext smaller than when you use this Edwards curve or this ED25519. Okay, good. But let's get back to business. Let's finish this detour. So how do we generate? So let's assume we have this group G and our generator lowercase g. And to generate public and secret keys, we just choose an X uniformly random from ZP, right? Something like 2 to the 255 minus 19, and set H to G to the X. Our public key consists of G and H, and the secret key just of X. So essentially, what you can think of the public key here is the first message in the this is the same thing actually as the first message in the Diffie-Hellman key exchange protocol. This is like the output of Alice1, right? Now encryption takes this public key GH and a message M, and now just does the following. Here it does something slightly different. It chooses a uniformly random Y and computes G to the Y and H to the Y times M. Okay, and the reason why I can just multiply M with this H to the Y is because I'm assuming that this message M is encoded in the group. Right? This is the traditional way of specifying the El-Gamal encryption schemes. There are other ways, but we stick with this simple version here. So decryption works as follows. Given a ciphertext C consisting of these parts C1 and C2, we just compute C2 times C1 to the minus X. Okay, and let's maybe quickly see why this is correct. So if you have a public key, this consists of G, and H equals G to the X. We have an encryption, C1, C2, right? Then if we write this encryption out, this C1 is just G to the Y, and C2 is H to the Y times M. So this is Enc. This was keygen. And if we look at decryption, it just computes C2 times C1 to the minus X. Now let's plug, let's just plug in definitions of C1 and C2. C2 is H to the Y times M times C1 is just G to the Y to the minus X. So now let's plug in the definition of H. This is just G to the X, but also to the Y times, let's pull forth this G to the minus Y times X times M. And of course, we see this G to the XY and G to the minus Y times X. These two cancel out. We just get M. Great. That's correctness of the Elgamal encryption scheme, but we also want security. So what does the following theorem state? So first we assume that the DDH assumption holds in this group G, or in this group ensemble, if we generate the group G on the fly in keygen, right? So we can either, if the group G is fixed, we assume it holds in this group, or if the group is generated by keygen, as I wrote it here, then we assume that it holds in this ensemble. Someone is asking, what was DDH again? Can someone from the audience answer? What's DDH? Thank you. This is the decisional Diffie-Hellman assumption. This is really just the assumption that the Diffie-Hellman key exchange protocol is a secure key exchange protocol. That's all, right? I mean, for us, in the last lecture, we simplified this to saying that G to the X, G to the Y, G to the XY is computationally indistinguishable from G to the X, G to the Y. Nothing happening so far, but here now G to the R for a uniformly random R. Okay, so this theorem says that if the DDH assumption holds, then the Elgamal encryption scheme is in CPA secure. And I mean, typically we would now again go through the full procedure with reductions and whatnot, but let's speed this up today because I still want to get into another topic. Let's first write the int CPA experiment down with the algorithms of the Elgamal encryption scheme actually plugged in. Okay, how does the in CPA encryption scheme look then? So Challenger first samples an X from ZP, sets the public key to G to the X, and the to h, which is g to the x, and the secret key is just x. The public key is given to the adversary. The adversary responds with two messages, M0 and M1. And challenger chooses a random bit B and encrypts the message MB. It means it chooses a uniformly random Y from ZP and sets our ciphertext C, which is C1, C2, to G to the Y, that's C1, and H to the Y times MB. This is a B. I actually call it C star. Now let's we give this C star to the adversary, who answers with this bit B prime, and we say when if B prime equals B. So now let me do an inline replacement. That's the INCPA security experiment. You've seen in essentially all the security proofs we've done so far, we went through these different thought experiments. And what we've done is we've modified this experiment to something I typically called X prime. Okay, and in this X prime, I am now going to do the following. So first of all, forget about the secret key. The INCPA experiment doesn't need the secret key. So out the window with the secret key, we don't need the secret key. By the way, here we should close this parenthesis. But now the next thing that I'm doing is here, I'm not using H to the Y, but instead G to the R, where I'm also choosing R from uniformly random from ZP. Okay, so instead of multiplying my message MB with H to the Y, I'm multiplying it with G to the R. So let's try to do this together. In this modified experiment X prime, what's the what do you naively or what would you intuitively think is the winning probability of the adversary? So how easy or how hard is it to win this modified experiment X prime? One half, someone writes in the chat, and that's correct. Since he gains no information with C star, this is exactly correct. So the probability that X prime outputs 1 is exactly 1/2. So this G to the R here, right? This G to the R, this is used nowhere else. You can think of this as a one-time pad acting on MB. Right, the other part that you learn, G to the Y, doesn't have anything to do with this R. So G to the R times MB is just a uniformly random group element, in fact, independent of MB. Good. So this modification made the adversary's life hard, actually not just hard, but impossible. Right now, in this X prime, the best thing he can do is random guessing. Okay, but how can I now argue that the adversary, when I change from the INCPA experiment to this X prime, that the adversary's success probability essentially doesn't change? So what could I do, or what would I do, what would I be enabled to do if A had substantially different success probabilities in the INCPA experiment and in this X prime? What could I do then? Good. Someone write, or two people wrote, then the DDH assumption does not hold. And that's this is correct. If someone were to give me some tuple G, H, G prime, comma, H prime, which is either, let's say, this is G, G to the X, G to the Y, and G to the XY, or maybe it is G, G to the X, G to the Y, G to the R. I don't know what it is, right? Someone just gives me these four group elements. I could do the following. Well, G is used as is, but now instead of choosing this H myself, I'm just choosing, I'm just taking this H from this, these four group elements that were given to me. So someone's asking a quick question: shouldn't you send in the picture back G to the Y instead of H to the H to the Y? Why not? Why not H to the Y? I mean, here I'm sending G to the Y, comma, H to the Y times MB. This is, I mean, the same as here, right? G to the Y, G to the Y and H to the Y times M. So, all right, good. But now H I can take from here. G prime, I can always write as some G to the Y. After all, it's a cyclic group, right? So whenever I'm using G prime, which I'm only using here, I'm taking this group element. And finally, H prime is either G to the XY. G to the XY is the same as H to the Y, right? Because H is G to the X. This I'm using as this group element here. Okay, so in the red case, it's G to the R. In the green case, it's just H to the Y. So if someone gives me these four group elements, I can just simulate this experiment and get that if I got something from the green ensemble, maybe an actual DDH tuple, then I have simulated perfectly the INCPA experiment. On the other hand, if I got some G, G to the X, G to the Y, G to the R, then I have simulated this X prime. And if the adversary was now acting noticeably different in these two experiments, I could actually use this power to tell apart these two distributions. Okay, so I want to leave it with this. I mean, from what we've seen so far in the lecture, you should be able to complete this into a fully fledged out security proof yourself. If you don't want to, just look into the lecture videos from last year. There I actually did it with all the details. Okay, good. Now let's quickly summarize this. Public key encryption allows for secure communication without prior interaction. I can talk to people who I've never met before, who I've never initiated a conversation with. So we've quickly talked about the textbook RSA scheme, and by modern standards, especially in terms of what it means to be secure, this is not an encryption scheme. It shouldn't be thought of as an encryption scheme, but more like a primitive or a building block. We will later see how to use this building block to do something meaningful, but the textbook RSA scheme is not an encryption scheme. Standard notion of security for public key encryption is in CPA security. And here we have essentially just adapted the notion of private key encryption. Historically, the other way around, but who cares for now? And the El-Gamal encryption scheme is an in CPA secure public key encryption scheme under the decisional Diffie-Hellman assumption. In a way, it's just the Diffie-Hellman key exchange protocol rewritten as a public key encryption scheme. All right, so let's close with that and get into the next thing, namely, so now you've seen how public key encryption, or how we can construct a basic public key encryption scheme. Let's now see how to actually use public key encryptions, how to actually use public key encryption. So, and this leads us to a notion of something that is called hybrid encryption, right? So what's a hybrid? A hybrid is a mixture of two things. Like if you think about hybrid electric cars, those are typically cars that have a battery plus usually a gasoline engine, where depending on the circumstances, we're using either power from the battery or from the gasoline engine, right? So hybrid means a mixture of two things. And hybrid encryption is, as the name suggests, a mixture of two kinds of encryption scheme. But I'm getting again ahead of myself. What I haven't been talking about so far is that public key encryption is expensive, and in fact, incredibly expensive. It's 2 to 3 orders of magnitude slower than private key encryption. So as an example, if you take a modern CPU, AES, there was an advanced encryption standard. We said it's this pseudo-random permutation primitive. So when you encrypt with AES in your favorite mode of operation, let's say counter mode, the encryption rate is typically something, I got this from the internet last year, something around 700 megabytes per second per core. So a single core, typically computers on a quad or octo core, a single core can gobble up 700 megabytes per second and turn that into ciphertext. That's all right. Someone is asking, is that AES figure with AES instructions of pure software? I guess so. Yeah, no, that's actually a good question, because these days cores actually have AES on chip. So it could be that this is software, and that, yeah, typically hardware AES instructions are even faster. Don't nail me down on this, but hardware AES encryptions are, at least in specialized hardware, somewhere in the tens or 20 of gigabytes per second. So I think this is a software figure, but please don't nail me down. On the other hand, when you compare this to RSA, say textbook RSA or Diffie-Hellman, doesn't make a big difference. This encryption rate drops down to 1.5 megabyte per second per core. This is more than 2 orders of magnitude, right? More than, or phrased differently, private key encryption is more than 100 times faster than public key encryption. That means, for all practical purposes, public key encryption is really, really expensive, right? So you typically want to limit the amount of public key encryption operations you have to do. Because 1.5 megabytes per second, I mean, that in these days at least feels slow. When you have a progress bar which runs up at 1.5 megabytes per second, that feels slow. Right, so think about encrypting your entire hard disk with RSA at this rate. Takes forever, right? Encrypting a terabyte at 1.5 megabytes per second, that's painful. Okay, so what do we do? What do we really do in the real world? So obviously, no one wants to put up with this snail speed of encryption. The immediate idea is, of course, combine public and private key encryption to get the best of both worlds. And what does that mean? The basic idea is for every new encryption or of some large amount of data, we first generate a fresh key K for our private key encryption scheme. Okay, then we take our private key encryption scheme with this key and encrypt our large message M. So I think M is this huge block of data. We encrypt this with our private key encryption scheme. Okay, but now what do we do with this key K? I mean, now let's say our receiver doesn't know this key K. How can we tell the intended receiver who only has a public key about this key K? We just take this key K and encrypt it under our public key encryption scheme, right? So take a public key. Now this key K is the message that we encrypt under our public key encryption scheme. And how big is this key, right? Here it says 0, 1 to the lambda, but I mean, size of K, let's say for typical AES is something like 256 bits. And then we can encrypt really fairly fast at 1.5 megabytes per second, right? Such a small key of just 256 bits is encrypted super fast. And my final ciphertext now consists of these two parts. I mean, let's draw them to proportion. C2 is essentially as big as the data we encrypt, and C1 is tiny, right? This just encrypts a tiny key. Sometimes we call this part the ciphertext header. It doesn't include any actual information about the message we encrypt, but just information that will later allow us to decrypt, and we call this C2 the ciphertext payload. Because this encrypts the actual message. Okay, let's quickly run through the advantages of hybrid encryption. Key is short, I've said that already. So the expensive public key operation is only performed on a very tiny message. The heavy lifting, encrypting the actual data, is performed by the super fast private key encryption scheme. Furthermore, this minimizes the size of the ciphertext for large messages and therefore saves bandwidth, right? Recall that for Diffie-Hellman encryptions, Elgamal encryptions, our ciphertext had this form C1, C2. C1, C2, and this size of C1 was a security parameter, or roughly security parameter, because it was a group element, and size of size of C2 is again also something like security parameter. So with Elgamal encryption, in order to encrypt lambda bits, I need to send you 2 lambda bits, right? A ciphertext of size 2 lambda bits. That's kind of wasteful, right? If I want to send you 100 gigabytes and I actually need to send you 200 gigabytes because my encryption scheme blows up ciphertexts. With private key encryption, this is not the case. The constructions that we've seen of private key encryption, like the let's say the counter mode, there the size of the ciphertext is essentially the size of the message. So someone asked a question in the chat and already got an answer. Is this hybrid approach used in the real world? Yes, totally. I mean, this is used in almost every application where you encrypt more than tiny amounts of data. So as soon as you encrypt, let's say, more than a kilobyte or more than, let's say, 10 kilobytes, it's advantageous to use hybrid encryption. For instance, in the transport layer security protocol. Okay, here's a quick example, right? How is hybrid encryption used? Someone writes also in Secure Shell. Let's say you want to stream a movie from Netflix, right? Then, this is done via public key encryption, but of course, in combination with secret key encryption via hybrid encryption. So Netflix first sends you the ciphertext header, which encrypts under your public key, right? A symmetric key K, and then it streams to you the actual movie encrypted under this private key K, right? So for that, it uses a mode of operation that's streaming compatible. No, this is not the "I did not hit her" scene. This is, oh, hi, Mark. Yeah, it. All right, good. I see there's connoisseurs in the audience. Okay, but let's quickly look at the size of or the ciphertext rate of hybrid encryption. The ciphertext rate is essentially size of ciphertext divided by size of message. And here, this is what's the size of the ciphertext? This is essentially size of the header, C1, which is small, plus essentially plus C2, which is essentially size of message. So this is this C1 divided by M, but C1 we said is small, so the ciphertext rate is essentially 1. So encryption doesn't, for sufficiently large messages, right? We always need that M is sufficiently big for this. Once the message length is sufficiently big, we're essentially not paying anything for encryption in terms of communication. Of course, there's a computational overhead, but it doesn't hit our communication bandwidth. Okay, good. As we've seen, hybrid encryption, we're just encrypting keys in the public key encryption scheme. We're not actually encrypting, say, meaningful information, right? And this leads to the notion of key encapsulation. So this is also another notion you should have heard or you should have at least met once when graduating from this course. So in hybrid encryption, we're just using the public key encryption scheme to encapsulate a randomly chosen key K, right? So we wrap this key, transport it securely to the receiver, who unwraps it and then decrypts the payload data, which is given to him. So this encapsulation is yeah, just another technical term here. But good. And in a way, this even leads to a simplification of the notion of public key encryption, which is called key encapsulation, or a key encapsulation mechanism. What that means in a nutshell is that the encryption algorithm of public key encryption is just replaced by an algorithm which samples a key K, which I can then use for private key encryption, and outputs a ciphertext C, which encapsulates this key. So basically, all this means is I'm putting these two steps of first sample a key and then encrypt it under public key encryption into one step, because that can be done more efficiently, as we will see in just a moment. We can even save another small amount of bandwidth and computation time with this idea. But this is a very small and moderate amount. So really, instead of an encryption algorithm for our public key scheme, we have now an encapsulation algorithm, which takes as input just a public key and outputs two things. It outputs this randomly chosen key K and the ciphertext's header C1, which encapsulates this key. And then, of course, in hybrid encryption, we can use this key. We can just use this key K, feed it directly as key into our private key encryption scheme, and use it to encrypt our actual payload message. All right. So really, this is just a small improvement, right? Versus choose your key yourself and then encrypt it under public key encryption. But since this is so ubiquitously used in practice, we need to discuss it here. So typically, the idea of key encapsulation allows for a small, roughly factor 2 size and efficiency improvement, as the ciphertext header doesn't need to encode arbitrary user-chosen messages. Okay, and let's quickly, really go through the syntax. So a key encapsulation mechanism consists of a 3 PPT algorithm. Keygen is the same as in public key encryption. Ncaps now again only takes as input a public key, but outputs a ciphertext C and a key K. Decaps takes the secret key that was generated by keygen and a ciphertext C, and decapsulates this same private key K. All right. Correctness is, of course, as usual. So if I generate a key pair PK-SK and then then create a fresh encapsulation of a key K, this should be a big K here. Then if I decapsulate the ciphertext, I will get the same key. Okay. Now really think about, you can think about this as a public key encryption scheme, which only encrypts random messages that the public key encryption algorithm, which is here called Ncaps, chooses itself. Okay, I mean, in CPA security is now slightly defined slightly different, because of course there's no messages involved, right? The adversary doesn't get to choose messages, which make things again even simpler. Challenger chooses a key pair PK-SK, encapsulates fresh key K. Now it chooses a bit B. If B equals 0, then it just sets K star to this key we just created with the encapsulation algorithm. If B equals 1, we choose a fresh and uniformly random key K star. Okay, so either we give the adversary the key K in case B equals 0, which is actually encapsulated in the ciphertext C star, or we give him a completely independent key. So now we give him the public key C star and this K star, and he of course has to guess B and wins if he guesses B correctly, right? So in the case B equals 0, K star is just the key, this C star comma K star is just the output of ncaps. If B equals 1, then K star is just something fresh and independent chosen. There's a question on the chat. What does encapsulation mean? Is it equivalent to encrypts too? So, I mean, it's just another word to disambiguate encryption, which is typically encrypting or enciphering meaningful information to just encrypting something random. Right, where encapsulate is, I mean, in a way, what it typically means in crypto. But again, this is just a assigned meaning. This is not that this is the natural meaning of the word encapsulate, which is just another word of wrapping something up in something. In crypto speak, encapsulate just means generating or sampling a ciphertext together with a random message it encrypts. This is really just a assigned meaning. And of course, getting back to the definition, oh, good. There's two more questions. Should ncaps encapsulate the secret key? No, we have two different secret keys here, right? There's this symmetric key K, which we wrap up in this ciphertext, and the secret key of this key encapsulation mechanism, or KEM, which can be used to decapsulate these ciphertexts. So no, we don't want to encapsulate this secret key. Someone asks here, A is something like a distinguisher here. Correct. So A just has to distinguish what we could even call him D here. And the security definition now sort of just asks for any PPT adversary A, the winning probability should be negligibly close to 1/2. As usual. Okay, that's key encapsulation mechanisms for you. Really, I mean, conceptually, it doesn't add anything. We're just discussing this because in the real world, these things are used, and you should, after graduating from this course, at least have heard of this notion of key encapsulation. Okay. But now let's quickly run through some examples. There's, of course, always the trivial key encapsulation mechanism, which doesn't offer any benefits. Give me a public key encryption scheme, and I can turn it into a key encapsulation mechanism by, doing the following. My encapsulation algorithm just chooses a key, a random private key K, and encrypts it under PK and outputs C, K, right? This is what I would refer to as the trivial KEM, because it really just uses a public key encryption scheme in the obvious way. The decaps, we just decrypt the ciphertext C. Okay, but now even more, every two-message key exchange protocol immediately yields a key exchange key encapsulation mechanism. And the example is the Diffie dash not equal Diffie-Hellman chem, where you do the following. My keygen just chooses a random x from ZP, computes H as G to the X, and outputs PKGH and SKX. Whoops. My encapsulation mechanism chooses a random Y, outputs and outputs a ciphertext C, which is G to the Y. And here you see the ciphertext doesn't consist of two group elements, but just of one. And K as my key K is now H to the Y. What does decapsulation do? Takes the secret key and C, and the secret key is of course X, just computes C to the X. So these three algorithms, have we seen them before? Do they look familiar? This keygen, ncaps, and decaps. Dramatic break. This is, so someone writes it in the chat, this is exactly the Diffie-Hellman key exchange. So this was the Alice-1 algorithm, this was the Bob algorithm, and this was Alice-2. This is precisely Diffie-Hellman key exchange. Okay, and again, as already observed, ciphertext is only one group element as opposed to ElGamal, where the ciphertext consists of two group elements. The NCPA security of this chem follows really immediately from the security of the Diffie-Hellman key exchange under DDH, right? Under DDH, where we remember DDH assumption is just the assumption that Diffie-Hellman key exchange gives us a secure key exchange protocol. All right, good. But now to the important part of this lecture, namely public key encryption, building public key encryption from a key encapsulation mechanism and private key encryption. So let's assume we have a key encapsulation mechanism, keygen, ncaps, decaps, and a private key encryption scheme, EncDEC. So now we're constructing a, and we've basically already seen this, a public key encryption scheme, keygen prime, enc prime, dec prime, as follows. Keygen prime just runs the keygen of the key encapsulation mechanism. Encryption first encapsulates a fresh key K in this ciphertext header C1 by running the ncaps algorithm, and then uses the enc algorithm to encrypt the payload message M and outputs this ciphertext C consisting of C1 and C2. Decryption does, again, the obvious thing. It first decapsulates the key K from the ciphertext header C1, and then uses K to decrypt the ciphertext payload C2. Right? We're doing really the obvious thing here. We're just using the key encapsulation mechanism to securely transport this private key, capital K. Okay, and now, I'm actually sort of going through this rather quickly, but I just wanted to, so that we're getting on with our program, I wanted to finish this part of the lecture today. We have the following statements, or the following theorem. Let's assume that a keygen, ncaps, decaps is an int-CPA secure chem, and that EncDEC is an int secure private key encryption scheme. It doesn't even have to be int-CPA secure, right? because spoiler, we only use the key once. So this just has to be insecure, not even in CPA. Let's maybe write that explicitly here, not even in CPA. Then keygen prime, enc prime, det prime is an in CPA secure public key encryption scheme. Right, and again, why is insecurity sufficient? We're just using this key K once, right? So under the key K, we will see you will just get a single ciphertext. So, and as last time, let's again just look at the interesting part of the proof. That is, let's write down our in CPA experiment for this keygen prime, enc prime, dec prime, and plug in these algorithms, right? How we compute keygen prime, enc prime, and det prime. So Challenger does what? First, computes PK SK using the keygen of my key encapsulation algorithm. Of course, now the public key is given to the adversary, who chooses two messages, M0 and M1, chooses a random bit B, 0, 1, and encrypts the message MB. And how does that work? Well, first we encapsulate a such a key K here by running the encaps algorithm. Encaps PK. Next thing, we compute our C2 as enc using the private key encryption scheme, using now this key K here of the message MB. And you know what? Let's be a little bit more explicit here and write our key K here in green, right? So we first create this green key K using encapsulation, and then we use it to encrypt MB and get our C2. And what we're sending back is, of course, the challenge ciphertext C star, which consists of C1, C2. My adversary, as usual, outputs a guess B prime, and we have win if B prime equals B. Okay, good. So that's the experiment for you. What do we have to do now? What will we do now? What? Let's try to do this together again. What would in your gut feeling be a reasonable thing to do now? Of course, we're switching into a thought experiment, right? We will have some exp prime. We will move to some exp prime, but what am I gonna change there? So what am I gonna do different in X prime? What could I do different? Please just speak up. If you don't want to speak up publicly, you can just speak up in a private chat message to me, and I'm going to read it. Okay, so the first person wrote something. Ignore the secret key. That's true. We can just forget about the secret key, we won't need that anymore. That's the first thing. Yeah, secret key is not needed in CPA security. Okay, good. What next? Aha. So someone wrote in the chat, replace K with a random key. And that's exactly what we're doing. So instead of using the K that was produced by the NCAPS algorithm, we just sample a uniformly random K from 0, 1 to the lambda and use this key K to encrypt our message MB. That's already it. So the first thing of course we have to show is that the INCPA experiment or the winning probability in the INCPA experiment is roughly the same or up to a negligible term the same as in X prime. Why is that so? How can we argue that? How can we argue that the adversary's winning probability doesn't change by a non-negligible amount when going from the INCPA experiment to this experiment X prime? How can I argue this? Security of what primitive do I have to use? Someone wrote NCAPS is random too, but let's be more specific. Which security property of which primitive do I have to use? NCAPS, that sounds already pretty good, but what security property do I have to use? What's the name of that security notion that I have to use? It's the, as someone wrote, it's the INCPA security of the CHEM, right? Via INCPA security of CHEM, right? And the way we do this, again, is, let's say, in the INCPA experiment of the CHEM, someone gives us a public key, let's call it C1, and a K star, right? And the difference only being in the this K star is either a random K or a key K where C1K comes out of NCAPS. PK, right? Down here, it's just a randomly chosen K. Okay? And what we do here, of course, is as in a reduction as public key, we're using the one provided here. As C1, we're using the one provided here. And as key K, we're using this K star provided here, right? So now again, we distinguish two cases. If K star is the green thing, then everything is green, so to speak, and we're just simulating the INCPA experiment. On the other hand, if K star is the red thing, then it's like everything is like in the experiment X prime. So an adversary that can tell apart the INCPA experiment, or that has different winning probability, substantially different winning probabilities in the INCPA experiment and the X prime experiment, can be used to tell apart or to win in the in the INCPA security experiment for the key encapsulation mechanism. But okay, good. This is this part of the reduction. Now let's say we are in X prime. What's the winning probability of my adversary in X prime? What can we say here? Now we still have to argue that his winning probability is negligibly close to 1/2 in X prime. And how do I do that? How do we establish that? How can I do this? Exactly. So someone wrote in the chat, it's 1/2 plus negligible because the encryption algorithm or the, let's say, the private key encryption scheme, EncDEC, is INCPA secure. So I just say notice in X prime, PK and NC1 are useless in the sense that they are independent of the actual ciphertext C2, right? Nothing about C2 ever goes out. Sorry, nothing about K ever goes out. Except for the ciphertext C2. So we can just use insecurity of EncDEC to argue that probability X prime equals 1 is smaller equal 1/2 plus negligible. And that's that. All right, that also finishes this sketch. And I actually got to finish all the things I wanted to finish. Isn't that great? So let's recap this lecture, and then we're already done. Hybrid encryption combines the advantages of public and private key encryption, right? The public key part is only used to transport a very small key, whereas the payload message is encrypted under a super efficient and super compact private key encryption scheme. For long messages, think of movies. This is essentially as efficient as private key encryption. So the cost of public key encryption here is completely amortized since both the communication and computational overhead of the public key part is so small compared to what the private key encryption needs to work. So key encapsulation mechanisms provide an efficient way to encrypt a random key, and typically this gives us sort of small but nice savings over just using any public key encryption scheme to encrypt this symmetric key K. And okay, that's all for today. Are there still questions to what we've seen today? So since there's only a limited number of lectures left, right? Let me quickly give you a quick overview what's going to happen. So on Thursday, we will talk about chosen ciphertext secure public key encryption. Next week, we will talk about digital signatures, and the week after that, Kas Kremers is going to show you how to bring all of this together. how to use this in actual real world protocols and standards. Great. Someone says, so 3 lectures left. No, if I count correctly, it should be altogether 5 lectures. I mean, 3 lectures left seeing my face, but then there's 2 more. All right. Good. Good. There's someone still asking a question. Is it not a problem that we use the red K in enc and output the green K to the user with encaps? Let's go here. Whoops. We're not outputting the green key K, right? So we're either using the red key or the green key to encrypt the message MB. In the InCPA experiment, we're using the green key, whereas in X prime, we're using the red key. So in the chat, I mean the information of green key in C1. This is the thing. This is precisely covered by by the security of key encapsulation mechanisms, right? If you look at this here, but that's a good observation. Here we're generating this C star with the encaps algorithm for the key K, and now for B equals 1, we're replacing K with a random key. So someone else is asking, how many tests are remaining? If I count correctly, it should actually be 3. So we're doing tests until in the last week. More questions. Will we get to get old exams to practice soon? Actually, yes, that's a good point. We're gonna let me just write that down. Put old exams online. More questions? Let me maybe, what's happening? Let's quit this. Good. All right. If there's no more questions, thanks everyone. Let's leave it with that and see you on Thursday.